So good afternoon. Thank you very much, all attendees, for coming to this 14th Fenix Infrastructure Webinar. Today, we have our colleague Benedikt Feldotto from the Technical University of Munich, and he will introduce the eBrain services deployed on ICEI Fenix infrastructures. So I only wanted to remind all the attendees that this session is being recorded and it will be shown later on the YouTube channel of the Human Brain Project. The link will be provided to you after the seminar. So now I'll give you the floor if you want to share your slides.
So thank you very much for the kind introduction, and thank you also for inviting me to talk about embodied large-scale spiking neural networks in the Neurobotics Platform in this webinar series. This talk will be all about large-scale spiking neural networks that are interconnected with a virtual body. This is what we call embodiment, and we do run all of these on a high-performance computing cluster in order to get scale and in order to get the performance that is required for the large-scale simulations. Everything that we are doing is centered around or implemented inside of the Neurobotics Platform. And the Neurobotics Platform, we call it short NRP, is one of the research platforms that we developed in frame of the Human Brain Project. It is part of the eBrain's research infrastructure and open to access for everybody with their dedicated account. Before we dive into the large-scale simulations, I want to get everybody to be on the same page here and give a quick introduction of what the Neurobotics Platform actually is. The Neurobotics Platform is a closed-loop simulation platform for embodied simulation experiments. It allows in silico experimentation of brain models controlling virtual agents in complex environments. So what we did is we connected community standards from different disciplines, such as NEST for spiking neural networks, Gazebo for physics simulation, and the robot operating system ROS for interfacing all of these components. There's a lot of other tools and services implemented, but these are the core components that we connect. We implemented a web-based interactive user interface so that people can, from home, from their standard laptop, access our platform via a web browser, use the simulation, and just like a game, inspect it and be inside of this platform. Everything that we do is open source, and you can install the platform as a local installation or as an online version. In order to facilitate good simulation design and execution, we also provide some tools such as the robot designer, an environment designer, and a virtual coach for scripted experiments. In a nutshell, the Neurobotics Platform is built up like this. It's subdivided in a front end here on the top, which is consisting of the graphical user interface that I already talked about. So really having some kind of 3D environment where an agent can move around and interact with an environment. But you can also use this Python script, which we call the virtual coach, to script automated experiment execution. The knowledge then, the computation is happening really in the background. And here we see that we connect those both worlds, the brain simulation in NEST and the physics simulation in Gazebo. Physics simulation means an agent interacting with an environment. And the agent can be either a robotic agent, for example, a classical industrial robot, or also a musculoskeletal system consisting of a skeleton and really biomechanical muscles. We implemented this closed-loop engine to connect and interface both these worlds so that we can read out the brain spikes from the left side and use it as control for muscles or actuators in the physics engine, and vice versa, read out sensory signals from robots or from muscles and feed them into the brain as spike signals. This is the current state of the platform that you can use locally or already online in the cloud via your web browser, but we now need to go further. And that's what the simulation or what the presentation here today is about. We want to use this Neurobotics Platform, the closed-loop simulation of body and environment, to really get at a scale, to really simulate a mammalian brain in the end. And here, for this presentation, we are talking about multi-region spiking neural networks at large scale, so talking about more than 1 billion neurons, more than 1 billion synapses. So what we need is a high-performance computing set on the one hand side, which can get quite complex. So the other goal is at the same time to be user-centric, so that it's really easy to use for any user from a standard laptop to access these resources, to access the simulation services, and have kind of a self-explanatory graphical user interface to run experiment that they need without any expert knowledge. So this presentation today is introducing the architecture and interfaces that we implemented and set up for the simulation service. We will then dive a little bit deeper into the multi-node brain parallelization, which is really doing the high-performance computing, the performant large-scale simulations. I will then show how the prototype looks like with a graphical user interface to set everything up. And then in the end, I will show a use case, a so-called Robobrain project, which is an embodied million neuron rodent brain inside of the Neurobotics platform and running on these HPC resources. Let's start first with the architecture and interfaces. We've seen that the software, the Neurobotics platform, consists of different tools such as Nest, Gazebo, and the browser interface, and many others. But now for the setup, for the large-scale setup, we need more tools or resources to actually make this happen. So on the left-hand side, we need additional compute resources that go far beyond the classical standard computer. So we make use of virtual machines on the cluster system, which are persistent. That means users can access them at any time. They are continuously running. And also we make use of compute nodes of the supercomputer Pistain, which can only be accessed on request. So we need to send a job request, and then we can use compute resources. On the other hand side, since we are embedded in the Fenix Research Infrastructure, we use the collaborative authentication so that users can have a login and then access the platform. We use the Harbor Docker registry to push our Docker images, so the software code, to easily pull them to our machines where we need them. And in the future, we'll also have secure storage and other tools. All these components together should then allow us for scalability in multiple dimensions. First of all, we want to implement the parallelization across cluster nodes so that we can simulate really large-scale neural networks. But at the same time, we want to have multiple concurrent simulations running so that an individual user or multiple users can run simulations at the same time on our service infrastructure. With these requirements and with these components, we came up with an architecture which looks like this. In blue, we see the cluster system, which again is the persistent virtual machines. And on the right side, there's the requested resources on the supercomputer Pistain. We have seen that the NRP is separated in the front end and back end. And here we even further separate them, having the front end running on a virtual machine, but the back end only running on a compute node on request. Since this makes the deployment a little bit more difficult or more distinguished, we started from the very beginning to really make an automated pipeline out of this to deploy the infrastructure on the dedicated systems. Starting from the developer source code, which is everything open source on Bitbucket, we have a continuous integration, continuous development pipeline that generates from this developer source code via Jenkins Docker images. We push these Docker images to the eBrains Harbor Docker registry to have them available and saved. And then either via Ansible, we do the machine configuration, so the setup of the virtual machine on cluster and pulling the front-end Docker image here. And on the other hand side, we use the NRP backend, pull it from Harbor, and then use it on the Pistain compute node on request, which is initiated by Unicore. This continuous integration pipeline has few benefits, and that is we can easily have continuous software updates. So if there is a bug fix or if there's a small change, we can easily change it in the source code, run the pipeline again, and have everything up to date. And we can also implement some kind of a version selection. So we can have in the eBrains Docker registry, have multiple Docker versions of multiple different versions of the NRP so that the user might select a version and can run the dedicated setup on the machines. So this is the NRP separated, but now since it's running on two totally different compute systems, we need to connect both of them. For this, we use Unicore, which is a REST API, that initiates, or first it communicates with the workload manager Slurm on Pistain HPC resources. And once this job is requested and set up, we establish an SSH tunnel that allows us for continuous communication in both directions, from the backend to frontend and frontend to backend, to really have an interactive online experiment simulation experience. Let's have a little bit deeper look in the Unicore REST interface. So I already said we connect the virtual machines with a Slurm cluster manager on Pistain. And basically we employ 3 different steps. That is, we launch the setup. So we launch all the architecture that I've introduced. Then we interact with the infrastructure, so we can inspect the jobs, we can see if the jobs have been successful or read the outcome. And in the end, we need to wrap up, so we stop the job so that no more node hours are consumed, and then we can clean up and delete all the files that we've used. All of these steps are subdivided in different functions that can be called, and every function is basically a Unicore REST call that consists of an authentication token that comes from the EBRAINS authentication, the parameters and the files, and as feedback we get the response in terms of description, files, or data. With this Unicore REST interface, we therefore can instantiate, control, and stop any job that is running on the state. Having the setup in place, let's look a little bit deeper on the actual multi-scale, large-scale compute resources. In our architecture on the right side, here, this is where the actual compute is happening. Yeah? We have a lot of cluster nodes, a lot of compute nodes that are scalable, that we use here and exploit for the simulation instead of a standard computer, which has been the previous case for the NLP on your custom or your own computer. So what we did is we implemented another REST interface that is interfacing the NLP. So the NLP got a Nest client interface, and this Nest client interface is communicating with the Nest server. So here again, we have 2 separate Docker containers. The NLP backend is running in Docker container. The Nest server is running in a Docker container, and a bidirectional communication protocol via REST API. Then again, the Nest server is not running on a single node because we want to distribute the brain computation across multiple compute nodes. And that's why there's one in Nest server, we have one master process, which is up here. And then there are several worker processes who do the actual computation of the Nest nodes and the Nest connections. We distribute the setup somewhat like this. So the user requests an arbitrary number of compute nodes. It needs to be at least 2. Because on the first compute node, we run the NLP with the Nest client, what you can see here on the left. On the second one, we run the Nest server and its master process. And then on every other compute node, there's 2 Nest worker processes running. As said, the user can customize the number of compute nodes, and with every other compute node, there's 2 more worker processes available for Nest. You already see we have implemented quite some communication interfaces, REST APIs, which are not particularly popular for being very fast. So the question is, does this actually make sense to distribute everything across so many different resources and compute nodes? Do we still get the performance gain that we want? And I can tell you, yes, we do. So what we did is we run a benchmark experiment on the architecture that I presented. And the benchmark is called the random balanced HPC benchmark, and is an equilibrium brain simulation that consists in our case of 225,000 neurons and 39 million connections. What we see here in the diagrams is on the left-hand side, only looking at the Nest server processes. In the previous slide, this was on the right side. So Nest is doing different procedures. First, it's creating the network nodes, then it's connecting these nodes, and then it's doing the simulation during runtime. We can see here, and this on the x-axis, we start from 1 single Nest process and scale it up to 64 Nest processes. What we see is a close to linear improvement in the computation time. So the The blue line here is the linear scaling, and you can't even see them here in the upper diagrams because it's so close to linear, the scaling that we implemented. This means, in other words, the creation time of the network took with one NES process about 0.4 seconds, and with 64 processes is taking less than 0.02, which is 20 times faster. The NES connection time is about 60 times faster than compared to one process and 64 processes, and the NES simulation time, so this is repeating every 20 milliseconds, could be reduced from 6 seconds to less than 0.1 seconds, so it's also more than 20 times faster. This is only the nest part, but also the nest part integrated in the neurobotics experiment. The overall experiment execution, that means launching an experiment, then having the interface between the body and the environment and the brain simulation, does also improve quite a lot. The overall runtime, which is launching and running the experiment, reduces from 500 seconds for one NES process down to about 40 seconds using 64 NES processes. So this is also more than 10 times faster versus distributed setup. At the same time, the real-time factor, this is interesting for interactive experiments. So how fast does this experience actually be in the end? We see a definite improvement from 0.01 up to about 0.14, let's say, with 32 nodes. We do see a saturation here. So there's only a small performance gain then to scale it up to 64 NES processes, but it's still improving. And our suspicion is that here the saturation comes because of the large inter-component communication that we established, but still for at least a scale up to 8 NES processes or even 32 NES processes, we see a huge benefit in the performance, which results in a faster execution time of the initiation and the runtime of the experiment. As I said in the beginning, this is to be served as an eBrains service. And you have already seen there's so many components included that it's quite difficult even for us as developers to set everything up. One approach is the automated deployment to make things easy for instantiation. But the other thing is that we implemented an additional graphical user interface, which makes it easy for the user to control all these architecture. So now we're talking about the left side, that is the front end that is continuously active on the customer virtual machine and the user who interacts with this front end. The requirement is it should be a self-explainable graphical user interface, and you should still be able to use the NLP interactively, just like a local installation. That means you can enter the 3D environment of the experiment and look around and change things on the fly. We came up with this user interface that does basically everything from the architecture perspective that I have introduced in the past slides. So it's split up in two parts. The upper part, here we have the setup job routine to specify the parameters of a job the user wants to run, then actually run the job with a button. And then the lower part to manage jobs, and here we can inspect the past jobs, the still running jobs, and the outcome of the jobs, the info and the terminal logs. Let's just have a look how this actually feels like. I brought a small video. So here you can see the user can select from a list of tunnel machines that we provide. Then he's specifying the job duration, how long does the experiment take, or how long do I want to use the compute resources. Then the user can select the node number, how many compute nodes do I want to integrate in the setup, depending on how large the brain is. Then I can also specify the memory per node. If I have a brain, I need the larger memory nodes. And then with a single click button here, I can set up the job. You can see here the process. So the job is now submitted. Once the job is accepted, the resources are allocated. We have an automated script that is setting up the NLP backend on the new compute node, that is setting up the tunneling machine, the tunneling between the NLP backend and the NLP frontend on the customer virtual machine. And also it's launching the Docker container of Nest server on the second compute node, again with all the worker processes on the given compute node number that the user has defined. So now the job has been instantiated and the NRP is running. We can see here a list of my past jobs that I have executed. And also here in the center, there's the still running job, which has just successfully been started. I have some control options here to get the info, get the details, and get the logs. So now we go to our experiment view. We see our list of experiment here. This is basically the standard NRP interface where the user can see his own experiment that he has developed in the past. And here we can see now our backends available. This is the Pollux, it's the old system. Now it's Castor, so the virtual machines. We have two virtual machine backends, which are the standard backends that any user of EBRAINS can use. But now we also have a Pistain job hooked in here. So now we can select as a backend the Pistain job that we have set up, an NRP running on the compute nodes, distributed on 5 compute nodes, and we launch this experiment on these compute nodes. Now the experiment view is loading, and you can see that we find ourselves in this 3D environment of the experiment setup. This is a really basic experiment. It's just our standard Brighton web experiment. So a few neurons connected so that the robot eventually moves to the screen, but only for the demonstration purposes. You see the experiment view, you can interact with the experiment, you can script it, define transfer functions, and so on. Keep in mind, here now we have 5 compute nodes in the back, each consisting about 72 CPU cores that this simulation can run on. So let's stop the simulation again. This is just for the demonstration purpose. We will see an example in a bit of time. It's finished. We can now start another experiment whatsoever. Go to the list of Pistain jobs. We still see it running because the job is still running and the backend is active. But now we don't want to consume any further compute nodes. So we stop the setup. And now after a short time, we see that the tunneling machine is available again. The resources are freed, no node orders are consumed, and also in our experiment view, we see that we have 0 backends available for Pistain. As indicated in the beginning, here now we could also set up multiple Pistain jobs at the same time, or multiple users can set up different jobs and use their backends to simulate their large-scale experiments depending on the configuration they want. How long the duration should be, how many compute nodes they need, how much memory they want to spend here. We have now seen the architecture, the distribution, and the interface. And the interesting now is what can we actually do with this architecture. So I brought for you here a use case that we call the Robobrain, because it's the Robobrain partnering project in frame of the human brain project that we are doing. And this is an embodied million neuron rodent brain simulation. So the goal of this experiment was to recreate a physical experiment in a virtual environment. So here we can see our 3D environment rendering. We have on the one hand side a body model that's consisting of a skeleton. And here for this experiment setup, we attached 8 muscles. These are hill-type muscle simulations. And you can see here the blue coloring is no activation and the red is an activation. And this mouse is embedded in an environment. So here, according to the physical experiment, we modeled a brain implement, an licomotor to really reward the mouse metal, a joystick that can move in 2 dimensions, and optionally there's an electromagnet here to apply some force to this joystick. So the mouse is able to manipulate this joystick in this 3D environment, and it's simulated with a physics engine in our setting. This is a body and environment model, and instead we connect this to a large-scale brain model. Here I introduce the multi-region brain model. You can see the wiring diagram on the left. I don't want to go into detail here, but the important figures are that we have a multi-region brain model that's consisting of basal ganglia, cerebellum, thalamus, sensory cortex, and motor cortex. And the total network size is more than 1 million spiking neurons, so biologically plausible or derived spiking neurons, and these are interconnected via 1.5 billion synapses. Given the NLP interface, the NLP architecture, we connect both these worlds now. So we have the brain model on the left. We use the transfer function framework to set up brain devices. They read out spike trains from the different layers here from the motor cortex, and these readouts can then be fed forward, used as an actuation command to control the muscles. Vice versa, sensory information from the muscles can be fed back through brain devices and fed back into the brain model. There's an optional state machine here that has some automated experiment controls so that you can apply some force to the joystick and hereby influence the experiment behavior. For this benchmark, we're doing the brain model and interfacing it via the musculoskeletal model by sending activation to the muscle group and activating the muscles. So how does it look like in the Neurobotics platform? Let's have a look at the online platform. This is really how it will look like. This is the web browser that you open and where we can join the experiment that is running on the supercomputer and then see what is actually happening. So in our experiment view, you can see here on the left our mouse model. On the right side, you see a spike raster plot. Just wait for the video loading. So here on the right, you see a spike raster plot, which is giving some insight in the brain activity that is happening. We down here, just for visualization purposes, have the client server messages. So that's the communication interface that we established. And on the right side, we can see the monitoring of the core activity that is happening in the background. What is happening here, the million neuron brain simulation is controlling the mouse forearm. And keep in mind that with this experiment, we have 1 million neurons in the background and 1.5 billion synapses controlling the setup. And it's running on the supercomputer sustained on several compute nodes. And hereby we can gain the performance in terms of the launching of the experiment and the execution time, so improving the real-time factor. At the same time, being highly interactive, joining the simulation, moving around here, changing parameters and changing configuration of the muscles of the interface between brain and body. So let's wrap up. What do we have seen in this presentation? Well, we've seen the first embodied million neuron brain simulation in the Neurobotics platform. The setup is only possible with a cross-platform architecture that's consisting of the NLP and Nest, and it's running on the Pistain supercomputer and multiple compute nodes, so highly distributed, highly parallelized. The setup itself is highly scalable, it's distributed and parallelized architecture and enables the high performance that we can see. This is only through this high performance computing it's possible to simulate this large scale experiments. And still we have a web-based graphical user interface so that users or EBRAINS users of the EBRAINS research infrastructure will be available to easily access our simulation services, access these experiment run and interact with the experiment online. The presentation here is the summary of the results of a lot of people involved. It's a very complex software framework. I would like to thank especially the last while developer team consisting of Jochen, Christian, Christopher and me who worked in the past to get this really done as it is here and running. Involved are mainly the CSCS Computing Center, which we like to thank, where we can run our simulations on and get the support for running the experiments. There's this Nest simulation team who implemented not only the Nest simulator, but also the distribution across multiple compute nodes. There's the Neurobotics Platform team for physics simulation, for the interface, for the deployment of the infrastructure, and the interconnection between brain and body. And finally, for the Robobrain model, we have partnered with some research institutes from Japan, from the Riken Institute, University of Tokyo, and the Okinawa Institute of Technology. And there's a lot of different tools involved, a lot of different aspects. So also thanks to everybody who contributed a bit or byte that I cannot mention here because it's just too many people that have contributed a little bit here. With that, I'd like to thank you for listening for the presentation, for the webinar, and I'm very open to answer your questions that you may have to this setup and experiments.
There is one question in the chat. So, did you offer ready body models or the user have to implement them too?
It's a mix of both. In the Neurobotics platform, we have so-called template experiments that are example experiments that people can just clone in their own storage and start working from those experiments and continuing them or changing them, improving them. But at the same time, users can also implement their own models. That's why we provide this robot designer, a tool to really design models from scratch. For example, this mouse model was designed with a robot designer to actually kind of draw with the graphical user interface muscles on this model to customize the experiments. From our view, it's very important that the user has control about how the body looks like, because in the frame of embodiment, what we call the closed loop between the brain and the body, we think it's crucial that the body, the role the body has, there's quite some controllers which have a low computation, but the sophisticated morphology of the body model can actually take over a lot of computation, and that's why important here. But to answer your question short, yes, there is some models, and since everything is based on community tools such as Gazebo, you can use also any Gazebo model that is available out there to be used in our Neurobotics platform.
And the same person that actually made that question raises another one. So if I have only a nest part, I could implement it with your platform?
Only a nest part does mean no brain model, no body model?
Yes.
So the focus of our platform really is to have the embodiment simulation, so the closed loop. This is at the core of what we are doing here. However, like the distributed setup of brain processes is also standalone available. There's also some Nest people working on that. So the first benchmark that you have seen, the HPC benchmark, has actually both a brain model and a body model, but those were not connected because this was a benchmark experiment. So there's nothing against just having a brain simulation and a body that is not connected within our framework. It is an overhead because we run the NRP, and that is all about this interface between body and brain simulation, but definitely it's possible. Maybe for you as a use case, it would be beneficial to start off with the brain simulation standalone and then take it into the NRP and then connect it in the end finally to a body model to see what the brain model is actually doing, what it's executing in the world, or vice versa, getting sensory data from a virtual environment. We also have a lot of different experiments where we just use the 3D theme as a data set generator, so having a visual information for looking around and feeding these into a brain model and see what we can actually learn with it, or what the brain regions do with this information.
Okay, thanks. So then we have two more questions. The next one is from Denise, who's asking, what are the next steps to make this available for all eBrain users?
So the platform is in place, the deployment is in place, and we've demonstrated with the benchmark that the architecture is working, and it's working very good, it's scaling very good. But there's an additional step to make this available to any user, and this has a lot to do with the global user management. So how can people access it? How can we make sure that the compute nodes are not for free? Compute nodes need to be requested and they need to be paid for. So there's quite some knowledge that needs to be implemented here in order to make this available to any user. And this is not standalone, but this needs to be implemented within frame of the eBrain's research infrastructure. So the efforts that will be made in the upcoming weeks is definitely about integrating a user control, a user authentication that is handling the compute resources, that is allocating compute resources, that is making them available, and then to use our platform. For test users, and we have had some test users from Nest or ourselves and from the NRP, we can already make the interface, the web-based interface available, and those who have the access data, they can already access it and use the simulation platform, but we now need to make it as a user accessible and also scale it up to have a lot of tunneling machines available for any user here.
Okay, then we address the third question. So thanks a lot for this presentation. I have a question regarding my trial to establish an experiment in our NRP, but I faced some issues to downloading some packages such as TensorFlow. Could you please elaborate on how to integrate these packages in an environment in NRNP?
So first of all, I want to say that this is a research platform, so not everything is going smooth because everything is under development, but that's why we want to create with the users a community to ever improve the platform. Please also have a look at our website. It's called neurorobotics.net, and you will find the links to actually install the platform as a local installation, as a Docker installation, or access the online platform running on virtual machines. And there you also will find the user forum. So please don't hesitate to go to the user forum, ask your questions if you have any issues, if anything is not working as expected, or if you need advice on how to implement an experiment or what tools are available here. In particular for the TensorFlow, the current platform, the current NRP version 3.2 that we use or that I have demonstrated here, is very centered around Nest, spiking neural network simulations, and body simulations in Gazebo. So for this online version, we don't offer TensorFlow currently, but you can install TensorFlow locally to use it. Actually, since it's based on Python, you can use any brain simulator that is available out there and install it. But I want to already say that we are working on the next 4.x version of the NRP, and here we have a more modularized interface so that we support a variety of brain simulators and also a variety of robotic simulators, so not only Gazebo but also Mojuko or OpenSim, because all of them have their own twist in terms of speed, in terms of supporting muscle simulations and stuff like that. So it will be made much more open. But for now, as said, if you have any questions or any issues, please don't hesitate to consult the forum that we have available, and the developers are very happy to answer your questions and help you with the setup.
So thanks. This question was addressed. Then finally, we have another one from Igori. Can we already find Robobrain example / tutorial on our NRP?
The Robobrain example, this Robobrain only runs on the HPC compute resources, because it's like, even though if you have the time, let's say, and you can run it very slow, it wouldn't work on a standard computer because we have a memory requirement of about 100 megabyte, and therefore it's still a research project. What we are currently doing is we are currently wrapping up writing the paper of this experiment. It will be submitted next week, and we have an open source repository where we then will link the code, or we will link the code so that everybody can have a look at what we did and reproduce it on.
Great. So I think we addressed all questions.
If there are any further questions anyway, as said, one option is the user forum, which is a technical forum, but also a support forum or a forum to discuss what is actually possible with the Neurobotics platform, what are features that are missing, what are experiments that you want to do. And on the other hand side, if you see there's potential, there's possibilities, or there's ideas of you who want to use the Neurobotics platform for your experiments, please don't hesitate also to contact us directly so that we can discuss with you on how your experiments can be implemented. And also if there are some potential collaborations, there's always some open calls within the frame of the Human Brain project where you can also allocate money to actually do the experiments and help you with the implementation.
So sorry, Benedikt, there is another question from Igori now. What is the title of the paper?
The exact title is, it's very similar to the presentation I had today. The paper will only be submitted next week, so I'm very happy to forward you, or maybe link to the, like this video webinar will also be released on YouTube, so for later view. And if I can link the paper when it's accepted, so that you can have a direct link to it and see the implementation detail. There will be also much more figures about the performance data, about energy consumption, about node hours, and stuff like that, so that you can have a deeper look. But it's deploying, I think it's deploying and optimizing a large-scale spiking neural network simulations on HPC infrastructure.
Okay, thank you. So then I'll take over and I'll remind all attendees about the Fenix services that we do have at the moment. So I'd like also to remind all the attendees about the services that we have in Fenix project. So we do have 3 types of accessing the infrastructure. So the first one is the HPP and the EBRAINS calls that they are already open, so there is no deadline. Then on the second one, we do have the possibility as well to have the praise ICEI calls, and the next one will be open on the 21st of March. You can also see them all. They are all always available on this URL, and the slides will be available as well on the page. One of the things that is important for us is your opinion, and we will send you an email after this webinar. So please fill in the questionnaire. It is really important for us to know what kind of things are important and what kinds of topics you would like to address for further webinars. And just to finish this webinar, I'd like to also invite you to our upcoming webinar that will be organized next week. And it will be also reminding everyone on how and when to access all our resources. So finally, I'd like to thank you, of course, today to our speaker, Benedikt. So thank you for coming and thank you for your time, and also encouraging all the attendees to join our Fenix user forum and of course stay connected in all our social media networks. Thank you.
Thank you very much. Have a good afternoon.